In this video, I want to take a look at one last type of quadric surface, and that is called the paraboloids. Now, there's two types of paraboloids. There's elliptic paraboloids and hyperbolic paraboloids. We'll start here with elliptic paraboloids. The thing about the equations of paraboloids is that they're fairly easily recognizable because two of the variables appear with squareds, and the third variable is only there in a linear sense, right? With hyperboloids and the ellipsoids that we've already done, the cones as well, all three variables appeared there in squared form, x squared, y squared, and z squared. Here, I'm only going to have two of them squared and one of them linear. And in that case, we generally write the equation in a way that we solve for that one linear one, and then write everything else on the other side. So the basic example here is z equals x squared plus y squared. Couple of things to notice here. If I look at slices, right, that for each constant value of z, at least for each positive constant value of z, like 1, you have 1 equals x squared plus y squared, or 7 equals x squared plus y squared, as each slice, horizontal slice, will be a circle. Right? Now, it's possible that you could have different coefficients in front of here. You could have 2x squared and 3y squared, in which case you'd be getting an ellipse for the cross-section. That's why they're called elliptic paraboloids. But in this case, it's a circle. In fact, if I click on this graph, I think that I can look at this in a 3D fashion. If I look straight down on this, you can see this is colored by height. So each color is a different height. Actually, each ring is a different height. And you can see those circles there for the slices for constant values of z. Yeah. On the other hand, if you look at constant values of x or y, right, if you take x equals 1, you're looking at z equals 1 squared plus y squared. Well, that's a parabola, right? And I believe if I slide down a little bit here, yeah, this graph is, it looks like it's squashed, but the scale is different here. It's the same thing, just squashed into view here. But you can see going in this direction, there's parabolas. Right? This is why it's called a paraboloid. Z equals a constant plus x squared on one side, or z equals a constant plus y squared on the other. And as you get different constants, of course, it's shifting it up higher or lower, which is why this goes up or down, depending on which way you're moving. And I can click on this one and see this in 3D. Right, you can see all those cross sections that are parabolas in the grid lines here in that direction, or if I move this way, you get it in that direction as well. Now, this is, if you take a look at this, the scale is vastly exaggerated, or condensed, I should say, in the z direction, right? Because this is, minus 5 to 5 in the x and y, but 0 to 50. If I were to, can I do this? I'm facing the way here. If I put the bounds on fixed, there we go, then you can see it in its true proportions, and it is really quite tall. Well, it goes up like a parabola does, right? A quadratic function grows rapidly. And as with the hyperboloids and ellipsoids that we saw earlier, you can stretch and scale this thing by replacing x by x over a and y by y over b, or z by z over c, right? So if I take the x here and say divided by 4, then it should stretch things in the x direction by a factor of 2. And if I look down on this thing, I think you can see now that the cross sections these way are looking like ellipses, because in the x direction it's stretched. Right? Likewise, I could stretch this in the y direction by, let's say, dividing by 9, so stretch it 3 in the y direction. So this has now been stretched both in the x and the y direction, and it's much wider. It opens more slowly because it's been stretched horizontally, x and y. And you can shift it, of course, if you want, by replacing the x by x minus h, and the y by y minus k, and the z by z minus l, just like we did in any of the other ones. Okay. Now, those were the elliptic paraboloids, because when you slice them for constant values of z, you're getting elliptical cross sections. Now, I say z only because this one was set up as z equals, right? The equation that I started with up here was z equals x squared plus y squared. If I had x equals y squared plus z squared, then this thing would be, rather than centered on the z-axis, it would be centered pointing out in the direction of the x-axis. Or likewise, if y was the one that was the linear term, then it would be pointing in the y direction. Now, a slight modification is what we get for hyperbolic paraboloids. Here I have z equals x squared minus y squared. Now, notice, if I take a constant value of y, say y equals 0, I get z equals x squared. So that's a parabola opening upwards. That would be a parabola going this way. If I picked a different value of y, say y equals, I think the edge here over here is 5, I'd have z equals x squared minus 25. And that would be this parabola down here on the edge. Notice it's opening upwards, but it's been shifted down 25. On the other hand, if I were to take constant values of x, like x equals 0, then I'd have z equals minus y squared, which is a parabola opening downwards, running right through the middle there. Or if I were to take x equals, out on the edge here, 5, it'd be z equals 25 minus y squared, so up 25, but opening downward. So in one direction, its parabola is opening upward, and on the other direction, its parabola is opening downward. This is like a saddle. I'm going to click on this thing and be able to look at it from different angles here, right? Opening upward in this direction. All of those grid lines are parabolas opening upwards. And then in this direction, all the grid lines are parabolas opening downward. Constant values of x in one direction, constant values of y in the other direction. A saddle. This is a hyperbolic paraboloid. Why hyperbolic? Well, the elliptic paraboloids, the elliptical part came from constant values of z. Now, the grid lines here don't readily show constant values of z, but the the surface is colored by height, right? So when you see all of that cyan, it's all the stuff at height 0. When you see this blue or magenta or red or whatever, these are different heights. And notice that for what's high? Which one's high? Okay, so the reds here are the highest and the oranges down there are the lowest. Right? So when I'm taking really big values of z, I'm looking at, my orientation is weird. I've got x going that way and y going this way. So let's put it more in the way we're used to looking at it, like this. So if I take big values of z, I have z equals x squared minus y squared. So with a positive value of z, this would be a hyperbola opening sideways, right? You can see that nice blue hyperbola going in there. It's probably elevation. Well, I have no idea what it is. On the other hand, if I took negative values of z, right, like -1 equals x squared minus y squared, well, multiply both sides by -1, and then you'd have 1 equals minus x squared plus y squared, and the hyperbola goes the other way. So the slices for constant values of z are hyperbolas, either opening one way for positive z's or opening the other way for negative z's. This, of course, can be stretched and squeezed and shifted just like any of the others. If I were to replace x by x divided by 2, this should stretch in the, come on now, move over. This should stretch it in the x direction by a factor of 2. So if I do that, well, it's squared, so I'm going to say divided by 4 here. Then that stretches it in the x direction. Now this looks a little funny just because the z coordinate is exaggerated so much, or condensed, I guess. Again, we're -5 to 5 in the x and y direction, but I'm minus 30 to positive 7-ish, right? So if I go to fixed, you can see better what this really looks like. So the shape, you can more clearly see the shape of the parabola in that would be the x direction, versus the shape of the parabola in the y direction, and it's definitely stretched in the x direction. Right? This is a skinnier parabola opposed to the wider parabola here in the x direction. But of course, we could, stretch things in the y direction as well by dividing by b squared, right? So again, if I were to say, let's divide by 9, so that would be a stretch of a factor of 3 in the y direction. So this is actually now stretched more in the y direction than the x direction. So there's the shape in the x direction. Get a sense of how wide it is. And then turn this way and see that it's actually wider in that direction. Okay. So it's very similar concept. Start with your basic hyperboloid, hyperbolic paraboloid, and stretch it, squeeze it like we did with the ellipsoids and the paraboloids. Now, as I'm moving this around, I notice one thing. Like the hyperboloid of one sheet, these surfaces are what are called ruled surfaces. In fact, they're doubly ruled. Through each point, there's 2 lines that are completely contained in the surface. So when I look at it like this and I see this pinch point, it means that there's a line that I'm looking straight down this line. Right? My pen is a line, but if I look straight down it looks like a point. And that whole surface, no matter how curved it is, it's coming right in and lining right up with that line. And so that's what I'm seeing as I look right down this pinch point right here. Now, I have another view of this that makes it a little easier to see the lines, because what I do is I'm going to take the standard z equals x squared minus y squared. I'm going to rotate it by an angle of pi over 4. Now, in order to do that rotation, we haven't done any of this, and I'm not going to test you on any of that, but it introduces an x times y, or an x times z, or y times z, depending on what combination of rotations you're doing. And then the coefficient depends on how much you're rotating. Anyway, there's some linear algebra that goes on here. There's some change of basis stuff that you can do with matrix multiplication and whatnot to describe it all and figure out what the formulas are. But yeah, there's probably even some eigenvalues involved, if you know what those are. Anyway, here's z equals 2 times x times y. Let's click on this and take a look. So, because this is turned by pi over 4, the constant values of x and y are now, well, they're still the grid lines they were before, but the way it was oriented before was the grid lines were showing the parabolas that you would see cutting across this one diagonally now. And what used to be diagonal is now vertical and horizontal on this. So each one of these grid lines, it turns out, is precisely a line. In fact, you can see that the equation here is z equals 2 times x times y. If you pick a constant value of x, then I've got z equals a constant times y, which is a straight line. Different values of x give me different constants that multiply by y, so it has a different slope. Right? And so you got positive slopes here, and then it goes down to slope 0, and negative slopes going down the backside there. Likewise, in the other direction, you've got positive slopes going this way, and then it turns into negative slopes, or the other way around. I might have myself backwards here, but certainly they switch as to what's positive and negative. Again, this is very much condensed in the z direction. To see it at its regular scale, I can switch to fixed here and see that this is really a very steep saddle. Yes, but it is ruled, and when you find one of those pinch points, it's because you're looking straight down one of those lines. I think it's easier to see those when you got it like this. You can see the different pinch points as I just rotate it up and down here. That pinch point moves its way across. Each time you see one of those pinch points, you're looking straight down a line that's completely contained on the surface. It is a doubly ruled surface. And you can see the double ruledness because both in the x direction and in the y direction, you have that same phenomenon happening. So lines going in both directions. So there we go. There are paraboloids, elliptic paraboloids and hyperbolic paraboloids.